Greetings, everybody. Hey, this is the brief lab that I promised you on lab number 5, the brief video I promised you on lab number 5, which is Kepler's laws. That'll appear in Canvas for you on Monday, June 8th, and it will be due on Tuesday, June 16th. I only have a few things to say about this, but this is a really interesting lab. There is some arithmetic in it. I'm going to show you how to do that too. But basically what we're looking at here is the sun and a planet going around it. This is one of the things you're going to verify in this lab, and that is what's called the equal areas law. And that simply says that when it's close to the sun, it's moving faster than when it's further away. So if we choose equal time periods, if we sweep out equal time periods between here and here and here and here, the actual area in this sector will be the same as the area in this sector. When you choose, keep this in mind now, when you choose where you're going to put your sectors, put them like this, separate them like this. Put one on one side and the other on the other side. Don't put them next to each other. That'll be much harder for you to actually, because you're going to be counting squares to actually estimate the areas. Now there's the equal areas law again. This is the second page, I think, where they talk about what eccentricity is for an ellipse. And here's what I was trying to tell you before. The area here, if the time between D and C is the same as between A and B, the areas here in these sectors have to be the same. That's the equal areas law. So pick them judiciously, and I'll show you how to do that in 2 seconds. In fact, here it is right here. This is the business part of the lab. This actually shows you the real orbit of Explorer 35 around the moon. Now, this is just an XY plot. Here's the x-axis. I cut it off there. Here's the y-axis right here. Here's the arrow showing the location of the moon. The moon is at one focus of the ellipse. And this is also the origin. And by the way, these numbers are in lunar radii units, okay? So that shows you how big the moon is in this idea. And these dots are actual locations of where the satellite was. Each of the dots are separated by 15 minutes. Okay, so that's telling you this thing was going at different speeds here and different speeds here. That's part of the equal areas law that you're going to verify. The first thing you need to do, though, is actually figure out where the major axis of the ellipse is. That has to be the longest line that'll separate the ellipse in exactly half. It has to go through this point because that's one of the foci. That's where the moon is. The center of the ellipse is going to be roughly about here. Don't quote me on that. You're going to be determining this. You're going to need a ruler and a protractor to do this part. So the major axis of the ellipse will look something like this. It has to go through that focus. You'll have to adjust it so exactly half the ellipse is here and half is over here. Halfway across is going to be the center of the ellipse, and you're going to be using a protractor to get a 90-degree angle so you can put the minor axis here. You'll see all these terms in the introduction to the lab on the first page. And then they're also going to have you measure this distance here from the actual orbit to this foci, and then over here on the other side on the major axis, you're going to be measuring it and showing where the other focus is. The moon is at this focus. There's nothing at this focus. It's important, by the way, you start off by actually filling in the orbit and drawing a smooth curve between all of these dots, because once you do that, then you'll be ignoring the dots and simply making your measurements based on the orbit right here. And I think for now, that's all I have to say about that. This is the other big enchilada. The first thing you do in this lab is verify that the orbit is an ellipse and verify the equal areas law. And then you do a really cool calculation. This is one of the interesting parts of this lab. Actually calculate the mass of the moon. And this is actually the expression one uses, and it boils down to this. Since the satellite's mass is negligible, you've got this is the mass of the moon equal to 4 pi squared over g times a cubed. A cubed is the semi-major axis of the ellipse, which you're going to measure, by the way, and p squared, which is the period of the orbit as well. And so I've done the first arithmetic for you. I did 4 pi squared over g. That's equal to this number, 5.91 times 10 to the 11th. And then you're going to have to take your data and cube the a and divide that by p squared. And for those of you that need a little help with doing arithmetic with exponents, I gave you a whole sheet on it that'll show you exactly how to do each step. What I want you to do, I prepared a little answer sheet. First, write down what a cubed is, write that number right here, then do the same with your data for p squared, write it right there. Then we're going to take a cubed over p squared, because that's what we want in the expression. You're going to put that on that line. There's another line further down where you can actually write the mass of the moon. So I want to see each step so I can make sure that everything was okay as you went along. And that's pretty much it. If you have any questions about any of the arithmetic or any of the steps, they're really well called out here, but send me a message.